we're talking about absolute or global extrema. Remember, extrema means either maximum or minimum. And you can say at x equals c, c is a certain value on the given interval, then we'll have maximum if f of c is greater than or equal of f of x on for all x in the domain. D is the domain, and minimum if f of c is less than or equal f of x for all x in D, where D is the domain of f of x. Okay, so this will be the definition of absolute or global extrema. And likewise, we wrote a definition for a relative or local extrema at x equals c. So, and by the way, by default, if you omit the word relative or local, we mean absolute or global. Okay, so here's a note. Maximum, what will be the word preceding?
What would be the word preceding?
Yeah, without the preceding word, maximum means absolute maximum, as opposed to relative or local maximum. So in other words, if we say just the word maximum or just the word minimum, then we mean absolute or global. Okay? So we use the, I guess the, is it an adjective in this case? I guess so. Relative or local. If we mean that. All right, let's write also, remind ourselves what is compared to the absolute. Again, with absolute we go with relative, or global we'll go with local. Extrema at x equals c. Our definition would be slightly different. The definition will read the following. We're going to say we have maximum or relative maximum. In this case I've specified if f of c is greater than or equal f of x for x on an open interval near C. Okay? And likewise, we're going to say relative or local minimum if f of c is greater than or equal f of x for x on an open interval near C. Okay. For keywords, open interval, near C, let's compare the absolute to the relative. Okay, so for the absolute is for all x in the domain. That's cut and dry. The relative is only on an open interval near x equals c, near that particular value that we are interested in. Let's go and do the first example. Let's look at the function f of x equal cosine x. And our task is to find its relative and absolute extrema. So find the relative and absolute extrema. So I need a line of separation here, like so. So let's look at the solution here. First of all, the cosine. Well, we know that the cosine function has a domain that consists of all the real numbers. The input x of this particular function can go from negative infinity to infinity, since we don't have any vertical asymptote in this case. Also, we know that the function itself is bounded by negative 1 and 1. So if this is y and this is x, so we know that at x equals 0, cosine of 0 equals 1. At x equals pi over 2 or negative pi over 2, the function equals 0. At x equals negative pi, or at x equals positive pi, oops, I missed that. The cosine equals negative 1, and so on. So it goes like this forever and ever, like so. Okay. I'll be a little fastidious here and use a whiteout to clean this sketch. All right. I've done better sketch than this one. So, where are the points of interest to us? Well, I can see that I have, based on this sketch, I have a local maximum right here, and right here, and right here. Also, what interests me in this case is that the slope of the tangent at this point, that is the derivative at this point, is 0, as the slope of the tangent, or the tangent, is a horizontal line. Okay, so in all these points of interest, we have horizontal tangent, or the slope of the tangent is 0, or the derivative at this point equals 0. And we see that we'll have maximum at 0. This point corresponds to negative 2 pi, and this point here corresponds to positive 2 pi, like so. This point is pi over 2, and this point is negative pi over 2, like so. So, we can conclude that starting at 0, every time we add or subtract 2 pi, we have a maximum. Now, is that a relative or an absolute? Well, the answer will be both. Okay, because there is no value greater than a cosine x equals 1. So we're going to say that we have a relative and absolute maximum x equal, we start with 0, right? And we keep adding 2 pi, 4 pi, and so on, or we're subtracting 2 pi. So it will be negative 2 pi, negative 4 pi, and so on. So we're going to say that x equals 2 pi times n, where n is an integer. So this will be the answer as far as where we can find the relative and the absolute maximum. And the value, of course, cosine of 2 pi n is always 1. So those are the values. Go ahead, Jason.
I think where you have pi over 2 should be pi.
I think you're right. Where I have pi over 2, I should have pi. You're absolutely correct. So, again, the white out we go, and we'll make this correction. Thank you, Jason. This is a very good observation. All right. We need to go to the next page to complete this exercise. What about the minimum? Okay, this was maximum. Going to say that we have relative and absolute minimum at. And now let's see, we have negative pi and positive pi and so on. So the next time up, if we go forward ahead, it will be 3 pi. The next time forward will be 5 pi. So we see that we start at pi and we're jumping to pi, which is one period of the function. Okay, and we know that this is a periodic function. It repeats itself every 2 pi. If we go to the left, we have minimum at negative pi. The next minimum will be at negative 3 pi and so on. So we're going to see that we have all the integer multiples of 2 pi, right? We start with, of pi, I'm sorry. We have 1 pi, 3 pi, 5 pi, negative 1 pi, negative 3 pi, and so on. The generator, the device that generates all the integers is 2n plus 1. So we're going to say that we'll have x equals 2n plus 1 times pi. Again, n equals an integer. Okay? Or the set of integer. So I need to write it as in a set form. So n can be negative 5, negative 3, negative 1, positive 3, positive 5, and so on. Okay, the values of cosine of 2n plus 1 pi is, of course, negative 1. So this was the deal for this particular function.